Table 310.7 in the National Electrical Code provides the ampacity of conductors in conduit. For 1/0 aluminum at 75 degrees Celsius in conduit, the ampacity is 180 amps. Industry charts may provide different ampacity values for aerial conductors. This is because aerial conductors have different cooling characteristics compared to conductors in conduit. The higher ampacity in industry charts reflects the improved heat dissipation in aerial applications. Table 9 in the National Electrical Code provides resistance values for conductors in conduit. Since triplex conductors are typically installed aerially, these values are not directly applicable. Resistance values for aerial conductors can be found in the appropriate industry standards or manufacturer's data sheets. The resistance of a conductor depends on its material, diameter, and temperature. The voltage drop on a conductor is determined by its length, load current, and resistance. The National Electrical Code requires that the voltage drop on any circuit does not exceed 3%. A fully loaded 1/0 aluminum triplex wire, 180 amps, can carry current for approximately 100 feet before exceeding 3% voltage drop. An 80% loaded 1/0 aluminum triplex wire, 144 amps, can carry current for approximately 125 feet before exceeding 3% voltage drop. Utilities may use different resistance values for aerial conductors based on their specific needs and operating conditions. These values may be higher or lower than those provided in the National Electrical Code. The National Electrical Code ampacity values for conductors and conduit are conservative and provide a safe operating margin for typical applications. However, for aerial conductors, higher ampacity values may be appropriate based on the specific installation and operating conditions. It is important to consult industry standards and manufacturers' data when calculating load currents and voltage drop for aerial conductors. To elaborate on the topic of triplex load calculations, it is essential to delve deeper into the various factors that influence the selection and application of triplex conductors. Firstly, let's address the ampacity of conductors. Ampacity refers to the current carrying capacity of a conductor, which is the maximum amount of current, measured in amps, that a conductor can carry continuously without exceeding its temperature rating. The National Electrical Code provides ampacity tables such as Table 310.16 and Table 310.17, which list the ampacity of different types of conductors based on their size, insulation type, and installation conditions. These tables are crucial for ensuring that conductors are not overloaded, which can lead to overheating, insulation damage, and even fire hazards. Secondly, the difference between ampacity values in the National Electrical Code and industry charts arises from the different installation conditions. The National Electrical Code tables are generally based on conductors installed in conduit or buried directly in the earth, which have less efficient heat dissipation compared to aerial conductors. Aerial conductors, on the other hand, are exposed to the open air, which allows for better heat dissipation. This is why industry charts often show higher ampacity values for aerial conductors than the National Electrical Code tables. It is important to note that when using industry charts, you must ensure that the specific installation conditions match the assumptions made in the chart. Thirdly, the resistance of conductors plays a significant role in voltage drop calculations. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends that the voltage drop on branch circuits should not exceed 3% and the voltage drop on feeders should not exceed 5%. The resistance of a conductor depends on its material, length, and cross-sectional area. Copper has a lower resistance than aluminum, which means that copper conductors will have less voltage drop than aluminum conductors of the same size and length. The longer the conductor, the greater the voltage drop. The larger the cross-sectional area of the conductor, the lower the resistance and the less the voltage drop. Fourthly, finding resistance values for aerial conductors requires consulting industry standards and manufacturers' data sheets. These sources typically provide detailed information on the electrical characteristics of conductors, including their resistance per unit length. It is important to use the correct resistance value for the specific conductor being used, as this will affect the accuracy of the voltage drop calculations. Fifthly, utilities may use different resistance values for aerial conductors than those provided in the National Electrical Code because they have different operating conditions and safety margins. Utilities often operate their electrical systems at higher voltages and with larger conductors than those typically found in residential or commercial installations. This allows them to deliver power over longer distances with less voltage drop. Utilities also have strict safety standards and procedures to ensure the reliability and safety of their electrical systems. Sixthly, when calculating load currents for aerial conductors, it is essential to consider all the loads that will be connected to the conductor. This includes lighting, appliances, motors, and any other electrical equipment. The load current is the total amount of current that the conductor will be carrying. It is important to ensure that the conductor is sized appropriately to handle the load current without exceeding its ampacity. Seventhly, the National Electrical Code provides guidelines for derating conductors under certain conditions. Derating is the process of reducing the ampacity of a conductor to account for factors such as high ambient temperatures, multiple conductors in a raceway, and the presence of harmonics. Derating is necessary to prevent conductors from overheating and to ensure that they operate safely. Eighthly, the length of the conductor is a critical factor in voltage drop calculations. The longer the conductor, the greater the voltage drop. It is important to keep the length of the conductor as short as possible to minimize voltage drop. Ninthly, the ambient temperature can affect the ampacity of a conductor. Higher ambient temperatures reduce the ampacity of a conductor, as the conductor will be less able to dissipate heat. The National Electrical Code provides tables for adjusting the ampacity of conductors based on ambient temperature. Tenthly, the type of insulation used on a conductor can also affect its ampacity. Different types of insulation have different temperature ratings. The higher the temperature rating of the insulation, the higher the ampacity of the conductor. In summary, triplex load calculations involve considering various factors such as ampacity, voltage drop, conductor resistance, and installation conditions. The National Electrical Code provides guidelines for calculating load currents and voltage drop, but it is important to consult industry standards and manufacturers' data when working with aerial conductors. Utilities may use different resistance values for aerial conductors based on their specific needs and operating conditions. By carefully considering all of these factors, you can ensure that your electrical system is safe, reliable, and efficient. The choice of conductor material, whether copper or aluminum, significantly impacts load calculations. Copper, with its superior conductivity, offers lower resistance, resulting in reduced voltage drop over longer distances. However, aluminum is lighter and more cost-effective, making it a popular choice for aerial conductors, especially in utility applications. When using aluminum conductors, it is crucial to account for its higher resistance compared to copper and to select an appropriately sized conductor to minimize voltage drop. The National Electrical Code provides tables that list the resistance values for both copper and aluminum conductors, which are essential for accurate voltage drop calculations. Understanding the concept of circular mills is also important in conductor selection. Circular mill is a unit of area used to express the cross-sectional area of a conductor. The larger the circular mill area, the lower the resistance of a conductor. The National Electrical Code Table 8 provides the circular mill area for various conductor sizes, which can be used to calculate the resistance of the conductor using the formula resistance equals resistivity * length/area. The resistivity of copper is approximately 10.37 ohms per circular millfoot, while the resistivity of aluminum is approximately 17 ohms per circular millfoot. These values are temperature dependent and are typically given at a standard temperature of 25 degrees Celsius. The National Electrical Code provides guidance on calculating voltage drop using Ohm's law, which states that voltage drop equals current * resistance. The voltage drop is typically expressed as a percentage of the source voltage. The National Electrical Code recommends that the voltage drop on branch circuits should not exceed 3% and the voltage drop on feeders should not exceed 5%. To minimize voltage drop, it is important to select an appropriately sized conductor, keep the conductor length as short as possible, and minimize the load current. The use of transformers can also help to reduce voltage drop by stepping up the voltage at the source and stepping it down at the load. Transformers are commonly used in utility applications to transmit power over long distances with minimal voltage drop. Harmonics can also affect load calculations and voltage drop. Harmonics are distortions in the sinusoidal waveform of the current and voltage. They can be caused by nonlinear loads such as electronic devices, switching power supplies, and variable frequency drives. Harmonics can increase the current flowing in the conductors, which can lead to increased voltage drop and overheating. To mitigate the effects of harmonics, it is important to use harmonic filters and to select conductors that are rated for harmonic currents. The National Electrical Code provides guidance on directing conductors for harmonic currents. In addition to voltage drop, it is also important to consider the insulation temperature rating of the conductor. The insulation temperature rating is the maximum temperature that the insulation can withstand without degrading. The National Electrical Code provides tables that list the ampacity of conductors based on their insulation temperature rating and the ambient temperature. It is important to select a conductor with an insulation temperature rating that is appropriate for the ambient temperature and the load current. The National Electrical Code also provides guidance on the installation of conductors. Conductors must be installed in accordance with the National Electrical Code to ensure their safety and reliability. Conductors must be protected from physical damage, moisture, and other environmental factors. Conductors must also be properly grounded to prevent electric shock hazards. Grounding is the process of connecting the electrical system to the earth. This provides a path for fault current to flow back to the source, which will trip a circuit breaker or fuse and to energize the circuit. Grounding is essential for protecting people and equipment from electric shock hazards. In addition to grounding, it is also important to use ground fault circuit interrupters, which are designed to detect small amounts of current leakage to ground and to trip the circuit. Ground fault circuit interrupters are required in many locations, such as bathrooms, kitchens, and outdoor areas. They are an important safety device that can prevent electric shock hazards. When working with electrical conductors, it is important to follow all safety precautions. Always to energize the circuit before working on it. Wear appropriate personal protective equipment, such as gloves and safety glasses. Use insulated tools. Never work on electrical equipment in wet conditions. If you are not qualified to work on electrical equipment, hire a licensed electrician. Working with electricity can be dangerous, so it is important to take all necessary precautions to protect yourself and others.